Hello and welcome to my presentation, which is about my study titled Orange-Red Phosphor Samples Applying to WLED made from RCFE combination, crystal form, and luminous characteristic. As far as we are concerned, the primary concerns for scientific study in the contemporary time are power saving, climate change prevention, and environmental harm minimization. To satisfy these necessary criteria, phosphor converted white light emitting diodes, which is also called PC white LEDs, which have safe energy, offer better performance, compact size, long lifetime, and environmental safety. Mixing a blue ingot chip with yellow phosphor samples is the economically most widely used technique for producing white illumination. However, there are downsides to this method. With the absence of red discharge within the observable spectrum, it used inferior chroma rendition index as well as an elevated correlated chroma temperature. Moreover, red emitting phosphor cannot be successfully simulated by NUV and blue LED chips. Lately, scientists have attempted to enhance white illumination output using one NUV LED chip accompanied by red, green, as well as blue phosphor samples. Additionally, this method suits the task of creating unique, non-organic red phosphor samples, having higher luminescence characteristics for extremely effective white LEDs. New orange-red RCF samples incorporated with Eu3 were created in the current work using a solid-state reaction technique because of their large bandgap, strong photochemical stability, and particularly small phonon oscillating power. For the crystal lattice work, fluoride-based host substances have received a lot of interest recently. Now we're moving on to the method stage where I will discuss the process of making RCFU phosphor, or abbreviated as RCFE. Solid state reaction was employed for creating multiple EU3 plus activated RCF phosphor in emit settings. The synthesis began with all the ingredients being weighed based on stoichiometric ratio. And the second step was grinding the materials homogeneously. And thirdly, the mixture was put inside one aluminum crucible, which is then put inside a furnace. Next, the mixture was heated under 1123 K within 12 hours. And finally, the product was cooled down to room temperature under swift chilling conditions, then grounded. As the first phosphor were made, various instruments were utilized to characterize this phosphor. First of all, these characteristics included phase purity, morphology and chemical composition, XPS analysis, photoluminescent excitation and emission spectra, PL lifetime, and thermally stimulated luminescence. As the process of characterization concluded, we move on to simulating white LED structure based on our white LED device used for the study here, which can be seen in Figure 1A. Figure 1B depicts a bonding graph based on the white LED device where 9 LED chips arranged in 3 parallel rows. And in Figure 1C showing the illustration for our white LED model. These rows are subjected to a yellow phosphor layer and a red phosphor layer, showing that we use the two layer phosphor setting for our white LED. And finally, in Figure 1D, we can see the white LED simulation made possible via the light tools application. As we concluded our task of WLED simulation, we move on to utilizing various mathematical expressions to gauge the performance for the created phosphor in a WLED device. First, we have expression 1 that determines the radius percent variation among the incorporated as well as possible substituted granules. In expression 1, CS signifies the coordinate value, and RH signifies the radius for phosphor-based granules, and RD signifies the radius for incorporating ions. Now we move on to expression 2 that computes the critical power shift range. In expression 2, V signifies the unit cell's volume. XC signifies an indicator of the Eu3 plus dope granules critical dosage, and N signifies the granule amount within a unit cell. As a result, the RC was determined to be 8.26 angstrom. The RCFE phosphor PL lifetime curves are measured at 515 nanometers and correlate to 394 nanometers for different EU3 plus ion doses. According to expression 3, a sole exponential function is used to fit the lifetime curve. In expression 3, A signifies a function for the fitting constants, which signifies the degradation duration, and IT and IO show the luminescence intensity under time t, and t equals 0. As a consequence of power migration into the EU3 plus ions, the finding demonstrate that the duration for RCFE raises alongside the surging EU3 plus granule dosage. As far as we are concerned, light emitting diodes require the chromaticity coordinates, which are a crucial component. The following expression 4 was used to determine the hue purity of the orange discharge for RCFE. In expression 4, XY, XI, YI, and XD, YD are correspondingly the hue coordinates for the discharge illumination, the similar power position, and the prevalent wavelength positions. RCFE phosphor has a computed color purity of 96.52%, which is considered to be great hue purity. After finishing the computation on performance of phosphor, as can be seen in figure 2, the presence of RCFE has a significant impact on the scattering features for the phosphor composition within the LED setting. In particular, the scattering coefficients increase with RCFE phosphor proportion. As a result, the light escape route will be changed in order to reduce the amount of light that is lost due to reflection and reabsorption. The luminous flux efficiency will rise as a result. Figure 4 and 5 show that CCT is concentration independent, whereas Figure 3 shows that the concentration for YGACE decreases with RCFE concentration increases. As seen in Figure 4, the phosphor may be able to reduce the variation in its CCT with further doping. The DCCT reaches the lowest value with 45% RCFE in Figure 5 at temperature of about 850 K. As shown in Figure 6, an increase in RCFE did not always mean an increase in the brightness of the white light emission. This displays a weaker blue emission and an uneven color distribution as a result of the greater backscattering and reabsorption. As the phosphor absorbs more backscattered blue light, higher RCFE doses in particular would encourage the light conversion from blue to yellow and orange, and phosphor coating starts to expand when the RCFE concentration is high enough. It was found that 45% of the RCFE was the best ratio for the simulated white lab to increase brightness and hue uniformity. The concentration of RCFE has a considerable impact on the brightness and chroma rendering for white LEDs, as shown by figure 7 and 8. The apparent declines in CRE and CQS could be attributed to unbalanced blue, green, and yellow-orange patterns. In order to control the CRE and CQS, this phosphor needs additional research on other features, such as particle size, which will be looked at in our research investigation. The emission spectra for RCFU-based white LED are shown in figure 9. The full range of white emission demonstrated the power of phosphor to intensify blue and orange-red light. The highest apexes would be located within the blue 450 nanometers, as well as yellow-orange, which is within the ranges of about 550 nanometers. And as we move on to our conclusion, the creation of the orange-red fluoride phosphor RCFE via the co-doping process requires a solid-state method under great temperature. And it is safer to assume that RCFE offsets the low red weaknesses of the white light generation method, thus yielding proficient white illumination. And on the other hand, they also have boost chroma purity, contributing to the overall color quality. And this is the end of my presentation. Thank you for listening.